Water, as essential to life as air. We couldn't survive without a steady supply of fresh, pure, drinkable water. When these gates were first opened in 1913, thousands lined the spillway to celebrate the completion of this California aqueduct. It carries water 240 miles, from the Sierra Nevada mountains to the thirsty city of Los Angeles. Even cities with lots of rainfall need huge dams and aqueducts to supply their growing population. This reservoir stores water for the city of New York, 100 miles away. The Romans built their first aqueduct around 300 BC. 400 years earlier, King Hezekiah of Judah had a tunnel carved through 1/3 of a mile of solid rock to bring water from a spring in the Ophel Hill to the pool of Siloam inside the old city of Jerusalem. The Bible tells of a blind man whose sight was restored when he bathed in this pool. Hezekiah's tunnel is famous for two reasons. First, for the debate concerning its sinuous shape, and second, for this stone tablet commemorating completion of the project around 700 BC. This is the oldest known cursive writing in the Phoenician Hebraic alphabet. It describes the triumphal meeting of the separate crews that dug from each end and finally came together. Although the straight line distance from spring to pool is only 332 meters, the actual length of the tunnel is 573 meters. Even today, water flows through this narrow tunnel. Its height varies considerably, from 1.5 to 5 meters, and it's barely wide enough for a person to walk through. We don't know the names of the engineers who built Hezekiah's tunnel, but the historian Herodotus tells us that 2 centuries later, in the 6th century BC, a remarkable Greek engineer, Ephpalinos of Megara, excavated a much longer tunnel straight through the heart of a mountain to bring water to the capital of ancient Samos. Samos is an historic Greek island in the eastern part of the Aegean Sea. Its area is a little less than 200 square miles, and it lies just off the coast of Turkey. It's a colorful island with high mountains, green valleys, lush vegetation, beautiful bays and beaches, and abundant wildflowers. This is the harbor of the ancient capital, now called Pythagoreon, after its native son, Pythagoras, who was honored by this modern sculpture. He's also remembered in other ways. The ancient capital was situated on the slopes of a mountain later called Mount Castro, which dominated the harbor below and the strip of sea between Samos and Asia Minor. These massive walls that rose over the top of Mount Castro and surrounded the ancient city are among the best preserved in Greece. As the capital city flourished in the 6th century BC, more fresh water was needed for its growing population. There was plenty of spring water north of the city at a hamlet called Agiades, but access was blocked by Mount Castro, not a huge mountain, but big enough to present serious problems. The contour lines on this topographic map show the altitude of points on the mountain. Along the 220-meter contour near the top, every point is 220 meters above sea level. That's a little more than 700 feet. The 50-meter contour is near the base of the mountain. Of course, the Greeks didn't have contour maps like this in the 6th century BC. They could make a rough map showing approximate locations without elevations. Probably there was a more or less level trail around the mountain, and undoubtedly people had climbed over the top and down the other side. Here's the problem they faced 2,500 years ago. The water is at Agiades. The thirsty people are on the other side. How do we move water from the source to the town with this obstacle in the way? Let's look at some possibilities. First, you could move the town to Agiades. But the people and their ruler, Polycrates, wouldn't stand for that. Second, you could try to bring the water over the top. But in the 6th century BC, the Greeks had no pumps or other mechanisms to do this. Third, you could go around with a canal. That was certainly within their capabilities. In fact, the Romans built such a canal a few centuries later to bring water from another source to these Roman baths near the seashore. But the Greeks didn't want a long, exposed canal that would be an easy target for invaders in Asia Minor, just a few miles offshore. What's left? Go through the mountain, and that's exactly what they did. First, they built an underground conduit from Agiades to the north face of Mount Castro, and then drilled a tunnel straight through the heart of the mountain, ending up inside the city walls. It gave them a subterranean delivery system completely hidden from enemies. The Tunnel of Samos was excavated by hand labor with picks, hammers, and chisels through more than half a mile of solid limestone. This was a prodigious feat. To speed up the process, 2 crews dug, one from each end, planning to meet in the middle, 150 meters below the top of the mountain. The big question is, how did Eupalinos figure out what direction the 2 crews should dig so they'd meet as planned? In modern times, digging a tunnel from both ends is almost a routine operation, whether it's a few feet beneath the streets of Los Angeles or 100 meters below the surface of the English Channel. Of course, ancient Greeks had no modern drilling equipment or surveying instruments, no magnetic compasses or theodolites, no radar or electronics, no helicopters or satellites, and no topographic maps. In the 6th century BC, they didn't even have much written mathematics at their disposal. Euclid's Elements, the first major compendium of ancient mathematics, was written some 200 years later. But some Greeks on Samos had contact with Thales, who lived at Miletus, on the mainland nearby. Thales used right angles and similar triangles to determine the height of a column by comparing shadow lengths. Armed with these intellectual tools and good common sense, Eupalinos pulled off one of the greatest engineering achievements of ancient times. How did he do it? No one knows for sure because no direct written evidence has come down to us from that era. But there are some convincing explanations, the oldest going back to Hero of Alexandria, nearly 600 years after the tunnel was completed. Hero flourished in Alexandria around 60 AD and founded the first organized school of engineering. The city of Alexandria had become the melting pot of antiquity, combining the intellectual heritage of the Greeks with practical knowledge from other cultures. Hero produced a large technical encyclopedia describing early inventions, together with clever mathematical shortcuts. He was noted for thinking up elegant theoretical solutions to difficult practical problems. This page from a modern edition of one of Hero's books describes a method for aligning a tunnel to be dug from both ends. Let's apply this method to the Tunnel of Samos. Start at a convenient point near one entrance and walk around the mountain along a series of right-angle traverses, staying at a constant elevation above sea level, until you reach a convenient point of your own choice where you would like the other entrance to be. By measuring the total distance moved west and subtracting it from the total distance moved east, Eupalinos could determine this distance, which tells how far east the southern entrance is from the northern entrance. Then, by adding north-south segments, he could calculate this distance, which tells how far south the southern entrance is from the northern entrance. Once Eftpalinos knew the lengths of the legs of this big right triangle, even though they were buried beneath the mountain, he could lay out smaller right triangles of the same shape on the flats to the north and to the south. For example, starting at the north entrance, he could walk along this survey line and pace off 1/5 the east-west leg to arrive at this point. He could then turn north at right angles and pace off 1/5 the north-south leg to this point. This would produce a small right triangle similar to the large one, but only 1/5 as big, with each hypotenuse on the same line. So the north crew could place markers along this hypotenuse and then look back at them to make sure they were digging in the right direction. In the same way, markers could be located along the hypotenuse of a small, similar right triangle visible from the south entrance to fix the direction for the other crew. Eftpalinos could also find the length of the tunnel before digging it by using similar triangles. By measuring the hypotenuse of the smaller right triangle and replicating it 5 times, he would find the length of the proposed tunnel to be about 1,036 meters, or nearly 2/3 of a mile, making it the longest tunnel built in ancient times. For Hero's method to succeed, 2 things must be done with precision. First, measure right angles, and second, keep at a constant elevation above sea level. Hero's book explains how you can do both these things with an instrument he called a dioptra. The dioptra could determine right angles accurately and could also be used to sight along a line of fixed elevation. However, most scholars today believe the dioptra did not exist in the 6th century BC. In those days, the Greeks had some way to determine right angles, as shown by the huge rectangular blocks on these beautiful walls that extended nearly 4 miles around the ancient capital. Moreover, dozens of right angles were also used just a few miles away in constructing a huge temple to the goddess Hera. To make right angles, Eftpalinos probably used a primitive tool, such as a portable rectangular frame like this. As long as the 2 diagonals are of equal length, the 4 corners are sure to be right angles. Even today, carpenters use this simple method to check right angles. For constant elevations, Eftpalinos could have used a simple water leveling device like this open rectangular gutter made out of clay. So even without the dioptra, Hero's simple but ingenious method, using similar triangles and gutters, explains how Eftpalinos might have solved the problem of digging a tunnel through a mountain from both ends, guaranteeing that the 2 shafts would meet in the middle. This convincing explanation was widely accepted for nearly 2,000 years, until modern historians began to question it. In the early 1960s, a British historian of science, Dr. June Goodfield, visited the Tunnel of Samos and studied the layout of the surrounding countryside to see whether Hero's method could have been carried out as suggested. She believed that Hero's solution, although mathematically elegant, would have been extremely laborious, or perhaps impossible, to carry out in practice. Why? First, there is a problem with the landscape itself. The southern entrance to the tunnel lies just above the 58-meter contour line. If you start from the southern entrance and try to walk along this contour line toward the western side of the mountain, you find extremely rough terrain, intersected by deep ravines. Dr. Goodfield thought it would take hundreds of horizontal and vertical measurements to lay out Hero's path with enough accuracy to determine the direction of excavation. She also pointed out a curious puzzle about the actual location of the tunnel. It was driven through the western part of the mountain, not through its center. Because Eftpalinos chose to enter further west, the underground conduit that brings the water to the tunnel from the north doubles back for several hundred meters before entering the mountain. And on the other side, the conduit to the town was correspondingly lengthened. If he had entered further east, he could have brought the water much nearer to its destination and shortened the underground conduits at both ends without lengthening the tunnel. Why did he not do so? Dr. Goodfield observed that the tunnel was built below the only place where one can climb easily up the southern slope and down to the north. She suggested that a row of markers could have been aligned by eye up one face and down the other to determine the direction of excavation. Going over the top of the mountain is certainly shorter than going around, but does it give the accuracy needed? To help resolve this question, Project Mathematics personnel visited Samos in the early 1990s to compare Hero's explanation with Dr. Goodfield's. The southern entrance to the tunnel is approached through this building, built in 1883, which lies near the 58-meter contour line. Inside the building, there's a narrow opening in the floor containing a steep flight of steps leading to a long, narrow, sloping corridor, barely wide enough for one person to walk through. The corridor was constructed to help camouflage the entrance after the main body of the tunnel was excavated. F. Polinos entered the mountain below the opening in the building, probably through an open trench closer to the 55-meter contour line. The trench was later buried and replaced by the corridor. Although the terrain outside the building at the 58-meter contour line is quite rough, just a few meters below, the ground is fairly level, and it's easy to walk along a goat path that traverses the southern face of the mountain. Further west, the terrain gradually slopes down into a stream bed that is usually dry. It's easy to follow this stream bed around the western face of the mountain to the northern face, which then gradually slopes upward toward the north entrance of the tunnel. So the nature of the terrain does not rule out Hero's method, which could have been carried out near the 45-meter contour line. Why did F. Polinos drill so far west and not through the center? It's possible he wanted to shorten the path around the mountain joining the two entrances. The point he selected for the southern entrance was inside the city walls, but as far west as possible. Did F. Polinos go over the top to determine the direction of excavation? It's not clear that he could do this accurately enough without instruments. And even if such a path could be laid out to fix the direction of the tunnel, he still faced another problem. To excavate the tunnel from both ends and be sure of meeting in the middle, it was essential that the two entrances be at the same elevation above sea level. Without modern instruments, measuring differences in elevation on a hillside is difficult and is bound to introduce errors, and the errors could accumulate as more and more measurements were made. So, how did F. Polinos solve the problem of elevation? No one knows for sure, but he could well have proceeded somewhat like this. First, he constructed the underground conduit to bring water from the spring to Mount Castro. For the north entrance to the tunnel, he selected a point that could be easily reached from the city. By marking a more or less straight path over the top and down the other face, he would want to locate the southern entrance at a point that was inside the city walls and had the same elevation as the north entrance. A sure way to determine this unknown point would be to start again from the north and construct a level aqueduct around the mountain, using water-leveling gutters like these to maintain a constant elevation. The point at which the aqueduct intersected the line over the top would be the location of the southern entrance, and if the aqueduct consisted of right-angled traverses, F. Polinos could use Hero's method to verify that he had an accurate fix on the direction for tunneling. No matter how it was planned, the excavation itself was an incredible accomplishment. Did the two crews meet in the middle as intended? Not quite. They would have if the diggers had kept faith in geometry. See how they started out, aiming precisely at one another. But as they approached the center, the crew on the north changed course and started to zigzag, first in one direction and then in another. Nobody knows why. Perhaps they were afraid they might dig right past their friends from the south and end up with two tunnels. As they got closer to the center, they zigzagged even more. But just as they were about to pass the other group, they heard the tapping of hammers. Both crews changed direction and made contact, a triumph worth celebrating. A visit to the tunnel today reveals its full magnificence. Except for some minor irregularities, the southern half is remarkably straight. Its 2-meter height and width allowed workers carrying rubble to pass those returning for more. The smooth ceiling is exposed naked rock that looks like it was peeled off in layers. Water drips through in many places and trickles down the walls. Calcium carbonate, the stuff from which stalagmites and stalactites are made, forms a glossy coating over most of the walls, but some original chisel marks are still visible. Because water will not flow in a level tunnel, Eftpalinos excavated a deep sloping channel below the floor of the tunnel along its eastern edge to carry the water from the north. Digging this inner channel by hand through solid rock was another incredible accomplishment, considering the fact that the channel is just wide enough for one person to stand in. Yet it is carved with great care. The tunnel floor is almost level throughout its entire length, but the depth of the water channel varies considerably, from 3 meters at the northern entrance to more than 9 meters at the southern exit. The entire delivery system was underground, completely hidden from unwelcome visitors. For centuries, the tunnel kept its secret. Its existence was known, but its exact whereabouts remained undiscovered. The earliest direct reference appears in the works of Herodotus, a full century after construction was completed. Physical evidence indicates the tunnel was used by the Romans and also in Byzantine times, but then it became neglected and remained lost until the late 19th century. An abbot from a nearby monastery discovered the north entrance and persuaded the Samos authorities to excavate it. 50 men went to work in 1882, clearing and restoring about half the tunnel. Shortly thereafter, the German archaeologist Ernst Fabricius surveyed the tunnel and published an excellent description, including this topographic sketch. Once again, the tunnel was neglected until the late 20th century, when the Greek government cleared the southern half, installed electric lights, and covered the channel with protective grillwork to keep visitors from falling in. At the north entrance, these modern stone walls lead to another flight of steps and another narrow corridor. Not long ago, this was the only way to enter the corridor from the north. Herodotus tells us that this tunnel was only one of 3 outstanding engineering achievements on ancient Samos. The Greeks on Samos also built an impressive seawall, still in use today, 2,500 years later, to protect their harbor. And a few miles to the west, they constructed a magnificent temple to the goddess Hera. It was one of the largest shrines of the ancient world, supported by 150 columns, each more than 20 meters tall. Today, only a single column remains standing. A few fragments lying about reveal the beautiful craftsmanship of that era, and they serve as silent reminders of the spirit and ingenuity of the ancient Greeks. This program describes an early application of mathematics to a question from real life. How can 2 crews dig a level tunnel through a mountain from both ends and be sure to meet in the middle? One method, proposed by Hero of Alexandria, calls for a series of right-angled traverses around the mountain from one entrance to the other, staying at a constant elevation. Measuring net distances in 2 perpendicular directions determines 2 legs of a right triangle, whose hypotenuse is the proposed line of the tunnel. By laying out similar right triangles at each entrance, the two crews can use markers to line up the correct direction for tunneling. The program explains how this could have been done using primitive tools available in the 6th century BC. Another theory states that a row of markers was placed over the top of the hill, along a line joining the two entrances. Although this seems simpler than going around, there are questions about whether this method is accurate enough to fix the correct direction and altitudes. No matter how it was planned, the completed tunnel is one of the most remarkable engineering achievements of ancient times. We've learned that common sense and a little bit of mathematics often help to answer penetrating questions about the world in which we live.